Okay, today we're going to start talking about gas stoichiometry. So let's read the question and let's see how we're going to attack this. Okay, a student places a small excessive aluminum metal in a sealed 750 milliliter container with 25 grams of hydrogen monochloride, HCl gas. All right, when we start talking about acids, we'll learn that to be also hydrochloric acid in gas form. The mixture was given time to fully react. The temperature was recorded to be 34.21 degrees Celsius. Okay, so predict the reaction. Okay, and then calculate the pressure in ATM of the gas produced in this chemical reaction. So we have a lot to do in this one little question. So let's first predict the reaction. So we have a piece of aluminum metal, and that's going to be solid, and it's going to react with the HCl, the hydrogen monochloride, or hydrochloric acid, whatever you want to call it, and that's a gas. Okay, so this is an example of a single replacement reaction where the aluminum will replace the hydrogen because the hydrogen is acting like a metal. Alright, so we get aluminum and chloride. Now, aluminum has a positive 3 charge, right, and chloride negative 1. So this is an ionic compound, so we have to go by ionic rules. And that's going to be a solid. And that hydrogen is going to kick off. Now, hydrogen, if you remember, is one of our 7 diatomics. And hydrogen exists as a gas at room temperature. Alright, so even at 34.21, obviously it would still be a gas, okay? So, now we have to go and balance this equation. You have 1 aluminum, 3 chlorines, so we might put a 3 here, but then you would say, well, how do I balance the 3 with the 2 hydrogens? Well, 3 and 2 is 6, so I'll put a 6 over here to balance that, and put a 3 here. Now we have 6 chlorines, we have 3 on this side, and oops, we put 2 there, and we get 2 aluminums now. So the stoichiometry for this reaction is 2623. Alright, so we predicted the reaction. Now we want to calculate the pressure in ATMs. Now, the other important piece of information that we're given is that we have 24 grams of this stuff, this hydrogen monochloride, and we have an excess of aluminum. That means all the aluminum will completely react. All right, there'll be a small excess, so some will be left over. Now, we could just do a mass-to-mass stoichiometry and figure out how many grams of hydrogen we made, but then that would kind of be defeating the purpose, because what we really want to know is the pressure. All right, so we're given a volume, okay, and we're given a temperature. So this is a direct application of the ideal gas law, which is the only gas law that you're really going to deal with moles. Okay, so what we really need to figure out is how many moles of that H2, because we could figure out the volume, right? The volume is 750 milliliters. We can't use that. And again, I'm going to skip steps that you should know. That's 0.7500 sig figs liters, because it has to be in liters for the ideal gas law. The temperature, it says it is 34.21. Again, we add 273.15 to turn it into Kelvin. And it's 2 places behind the decimal since we're adding. We get 307.36 Kelvin. All right, and we just need the moles, which we're going to find out. So we're going to do a little bit of stoichiometry to get those moles. All right, so we know that 24 grams of HCl. We have to convert that to moles because, listen, all you really need to for stoichiometry is that mole ratio. So converting into grams to moles is not stoichiometry. It's just a mole conversion. All right, I like to label things so I don't forget what things are. The molar mass of HCl is 36.46 grams. All right. So we want to know not how many grams of H2, because then we'd have to go back and convert it back to moles anyway. So let's just figure out how many moles of H2. All right, so what's the mole ratio? Well, it's 3 to 6, or 3 moles over 6 moles. You plug this into your calculator, and you should get to 4 significant figures over here. 0.3291 moles of H2. Okay, so now, again, we have these moles, and we can go and use the ideal gas law, all right, to figure out how many moles of or how many, what's the pressure given these sets of conditions. So remember, the ideal gas law is PV equals nRT. Now, I've heard some people call this PVNRT for short. So if you ever hear that, I really don't know where you're getting it from. I guess you can kind of analogize it to PVNRT, but so we are trying to find pressure. All right, so moving the equation around, P equals nRT over V. All right. So doing that, we want to plug in pressure equals N, which we just figured out to be 3.291 moles. Okay. And this is for the gas H2. It wants it in ATM, so we are going to use 0.0821 ATM times liters over moles times Kelvin. And then the Kelvin temperature we said is 307.36 Kelvin over the size of the vessel that it's in is 0.7500. You want to go hit pause and plug it in, see if you come up with the answer. Again, this is 4 sig figs. This is a defined quantity, so that doesn't count. This is 5. This is 4, so my answer should have 4 sig figs. And I believe if we do this right, 4 sig figs, we come up with 11.07 atmospheres of H2 gas. All right, so again, a pretty involved problem. Again, predicting the reaction, finding moles using these sets of conditions, applying to the ideal gas law, and then again, we want to find the pressure of this hydrogen diatomic gas. All right, so a lot to absorb. And again, you could also start with the number of moles and then go find grams. So again, just realizing that stoichiometry, okay, demands you to be in moles, because this right here, again, is the heart of it all. All right, that's the stoichiometry. All righty. So we'll give you one more question for you to work on that we'll go over together. I will let you try it first. All right, so fluorine gas was injected to the same vessel as in question number 1. Okay, 12.5 grams of the fluorine gas. So it's injected to the same vessel, I guess probably to some port. Assume the conditions are the same as well. Fluorine gas completely reacts with the excess aluminum chloride that was produced. Right, if you remember the reaction, we produced some aluminum chloride, and it reacted with fluorine. So you should be able to predict the reaction. Now it says calculate the partial pressure of the gas produced. Now for right now you're just calculating the pressure, all right? And I'll explain what partial means after you calculate it. So essentially do the what I did in the previous question to go calculate the pressure of the gas that is produced in this reaction. Okay? Alright, so hit pause and then we will come back and go over it. And I'll explain what C means as well. Alright? Okay, so we should be back by now. So anyway, let's predict the reaction. Alright, so fluorine reacts with the aluminum chloride. Now remember, fluorine is a diatomic gas. What type of reaction is this? Alright, it's a single replacement. Now, fluorine won't replace the aluminum, but it will replace the other nonmetal. So this is a nonmetal single replacement reaction. So fluorine kicks out chlorine, and we get chlorine gas. Okay, remember fluorine is a gas. And this is what we're trying to find the pressure of, right? It's AlF3. Again, fluorine's a -1 charge, aluminum's +3. Chlorine, though, is a diatomic gas like fluorine. So now we have to go balance the thing. So come with the factor of 6. So I'll put a 3 here and a 2 there. That balances the fluorines. And a 2 here and a 3 here. And my chlorines are balanced as well. So again, this would be a solid. Again, we're talking about ionic reactions. And that would be solid too. We're not dealing with wet chemistry here. So there's no aqueous in these reactions. Okay, but you could if you really wanted to. All right. Again, states right now are just, it's important you want to understand that chlorine is the gas that is made. All right. So anyway, we want to be able to again predict the number of moles. So again, define the pressure. So the temperature I believe was 307.56 Kelvin. The volume 0.7500 liters. That has not changed. Again, we need to find the moles via stoichiometry. So let's do that now. All right. So we got 12.50 grams of F2. All right. Fluorine's atomic mass is 19. So multiply that by 2, and we get 38.0 grams of fluorine for every 1 mole of fluorine. Right. And again, I just want to go to figure out moles of fluorine. I don't need grams of fluorine. Right. So the mole ratio between aluminum chloride and fluorine is for every 3 moles that react, you need 2 moles of aluminum chloride. Okay, and doing the math to, again, 4 significant figures would give you 0.2193 moles of F2. Alright, so we got 0.20, if you want to put the 0 there, no big deal, it's not important because it's not significant. So now we have everything to figure out the moles, all right, or to figure out the pressure of this Cl2. So again, pressure equals nRT over V, right? 2193 moles. Again, we want it in ATMs, 0.0821 moles, sorry, ATM times liters times moles times Kelvin times 307.56 Kelvin. Again, the volume is not changing. It's remaining constant. All right. And if we do this right, to 4 significant figures, because this is 4, again, this is 5, this is 4, you should get 7.383, okay, ATMs of the Cl2. Now, we call it a partial pressure because remember, we're doing it in the same vessel as the first reaction. Well, what else is in there? Okay, well, obviously there's going to be a little bit of aluminum solid that might be in there from the first reaction, but it's not hot enough for it to form a synthesis reaction. But remember, there is some H2 gas, right? And I believe it was like 11.07 ATM. So that hydrogen gas is also contributing to the pressure. All right. So when you have two gases together, all right, we take those individual pressures as partial pressure. Okay, just like the air we're in right now. The air is about 77% nitrogen and about 23% oxygen. Okay, so the pressure from the atmosphere, from the air, those two gases are contributing to the overall pressure. Okay, so if we have two gases that are in the same vessel, all right, and if we're looking at the pressures individually, we call those partial pressures. Okay, so calculate the total pressure of all the gases in the sealed container. That's pretty easy. So Dalton's law up here of partial pressure states that each gas will contribute to the overall pressure, and all you have to get the total pressure, call it P total, you just simply add up the gases. All right, 11.07 ATM plus, we just figured this out to be 7.383. All right, and I believe if we add this up, it should come out to be 18.456. I'm sorry, or 5.3. All right, so again, the two places behind the decimal, that has 2, this has 3, so we'll call it 18.45 ATM total pressure. All right, so that's pretty much Dalton's law of partial pressures and gas stoichiometry in a nutshell. Okay, and I believe this will be the last video for the gas series. All right, and any other questions, we'll deal with it in class, and hopefully we should be good. All right, thank you for your time.